Hello, my name is Kojo Orgo.
Hi, my name is Juma Mlawa.
Hi, my name is Yoel Gabrat.
Hi, my name is Marissa Offley, and we'll be discussing the use of multivariate regression for permeability estimation.
Today, I will be introducing the basics of permeability in petroleum engineering. Permeability is the capacity of a medium to transport fluids through a system of interconnected pore spaces. In reservoir dynamics, permeability is one of the most important rock properties, as it relates to the rate at which hydrocarbons could be recovered from a reservoir.
Here, we see a figure giving an example of flow through a permeable rock. Henry Darcy provided an algorithm describing the flow of fluids through interconnected pore spaces. Darcy's law comes to the conclusion that fluid flow in a reservoir rock is highly dependent on the cross-sectional area of the system, the total pressure drop across the system, the length over which the pressure drop takes place, the total discharge through the system, the viscosity of the fluid. These factors arranged by proportionality give the equation for Darcy's law. Permeability distribution in a reservoir is complex and depends on factors such as heterogeneity, where permeability is non-uniformly distributed through a reservoir. Additional factors affecting permeability calculations in a reservoir are the flow paths of the fluid through the reservoir. In parallel flow, the flow direction is parallel to the layers of rock in the reservoir. In series flow, the reservoirs have permeable rock systems that are arranged laterally, and the flow is perpendicular to the faces of the deposited rocks. Permeability is arguably the most difficult property of reservoir dynamics to determine or predict. Several approaches have been developed to better analyze well-logged data. Some of these methods include empirical methods, virtual measurements, and multiple linear regression. Multiple linear regression is often used because it is cheaper, easier to use, and the data is more accessible than the other methods.
With that being said, Juma will discuss more about the challenges of estimating permeability from well logs.
Companies working in the oil and gas industry are faced by a myriad of challenges and limitations, chief among which is how to maintain large capital investments and choosing which projects should have a higher priority when it comes to development. Estimating permeability from well logs using multivariate regression is no different. It too has its own challenges. So what are some of these challenges?
Firstly, many thermodynamic and kinetic data are not readily available. This data is key in quantifying mass transfer processes which may affect formation characteristics such as porosity and permeability. The second challenge is in obtaining a large number of core samples to effectively use multivariable regression comes with a higher cost bill for coring and laboratory analysis. Usually, cores are obtained from a few wells and predictive models are created to estimate permeability. However, in many frontier exploration and development markets, such as Southeast Asia and Eastern Africa, this cost may be even more compounded due to the fact infrastructure is a stumbling block and a mature supply chain is not present. As a result, major companies and independents operating in these new markets could possibly see their operating costs spiral out of control. Lastly, predictive models comparable to multivariable regression are sensitive to calibration dataset. For instance, in sandstones, a few things permeability is controlled by are grain size and orientation, bedding, cementation, and clay content. So, if a dataset mainly consists of data with little clay content, the resulting regression will not accurately estimate permeability in rocks with greater clay content in them.
Despite the challenges I just mentioned, this is one of the most effective methods out there currently. There has been a multitude of successes using this technique, providing practical estimates for permeability. To explain further about multivariate regression, I invite Yoel to speak more about this.
I'll discuss the methods that we use in the study as well as the results that we obtain from applying multivariate linear regression to our dataset. Multivariate linear regression provides a proven, quick, and computationally efficient method for obtaining permeability estimates. Our goal is to create a predictive model based on measured permeability values from parameters derived from well logs. The equation for multivariate linear regression is shown below. A dependent variable, y, is estimated based on a linear combination of independent variables, x sub p. The coefficients, b, are multiplied by the independent variables, which in our case are the well log parameters. By calculating the coefficients, we are able to create a predictive model. We are using the well log obtained from a carbonate reservoir. Core permeability and well log derived properties such as water saturation, porosity, depth, volume of dolomite, volume of limestone, and borehole diameter are displayed on the well log. A sample of the well log used in this study is shown below. This well log was digitized and the values were obtained in 0.1 meter steps. The R programming language is used to apply multivariate linear regression and generate the model validation plots. R is an open source statistical software that has gained a lot of popularity recently. In order for the use of multivariate linear regression to be valid, the dependent variable must follow a normal distribution. However, permeability often displays a log normal distribution. This means that we must apply data transformation to our data in order to obtain a normal distribution, or one that is approximately normal. The Box-Cox transformation searches for a lambda value that maximizes the log likelihood of a distribution, thus making it as close to normal as possible. We ended up choosing a lambda value of 0.16. This slide shows the results of applying the Box-Cox transformation in R. On the y-axis we have the log likelihood, and on the x-axis we have lambda. Our goal was to choose the lambda that maximized the log likelihood value, and in our case that was 0.16. On the right we have a histogram of the transformed permeability. As you can see, it is a much improved approximation of the normal distribution than what we initially began with. Below is the command used in R to generate our model. After running our model, an ANOVA table was used to see which variables are statistically significant and should be included in our model. The results of our analysis of variance table is shown below. In the circled column, we can see that all of our p-values are less than 0.05, which means that they are all statistically significant and should be included in our model. The results of our multivariate linear regression model are shown below. The estimated coefficients and the error associated with those estimates are shown in the two columns to the left. Now I'm going to pass it over to Marissa. She'll provide a summary of our results and discuss some of the strengths and weaknesses associated with the use of multivariate linear regression for permeability estimation.
Now we're going to analyze a few statistical plots to assess the accuracy of our estimates. We're also going to take into account other factors that affect the reliability of our model, as well as some of the pros and cons of using multiple linear regression for permeability estimation.
As you can see from the R-squared plot, we have a very strong correlation between the estimated and measured permeability values, although for the higher permeability values, the correlation is not as strong. For the residuals plot, our error ranges from about 0 to 15 millidarcy, which is fairly reasonable when using this technique. A drawback with this method portrayed in the QQ plot is that there is an overestimate of the low permeability values and an underestimate of the high permeability values, which is signified by the solid red line. This is generally the case for this estimation technique. An assumption that we made while using this method was the independence of variables with each other. With multiple linear regression, the independent variable should ideally represent statistically independent pieces of information. However, there is usually some interdependence among the independent variables. We also assume that these variables were actual measured values, when in fact they were calculated from well-log properties. In addition, using this technique, you assume that the variables are free of error, which is usually not the case for petrophysical data. A limitation of this method is the fact that we couldn't statistically predict permeability where fractures occur. In addition to that, the data is based upon a carbonate reservoir. Carbonate reservoirs exhibit highly variable properties within small sections of reservoir, which makes it difficult to compute an accurate measurement of permeability.